Welcome back to another exciting chemistry lesson. In the previous lesson, we learned about pH, pOH, and how they all relate together. And we also learned about equilibrium constant, how to write equilibrium constant. In this lesson, we are going to combine them together. That's why this lesson is the most critical lesson that you have to watch and really try to understand. Because this is where we're going to tie everything together. So first thing first, we know how to write equilibrium constant. The first thing we are going to look at the equilibrium constant for the self-ionization of water. That is, water react together. Remember, water can be both acid and base, right? They react together to produce the hydronium ions and the OH ions. So here we have Kw. What's W for? That's water. So Kw in this case is equal to the concentration of hydronium ion times the hydroxide. Now, in some cases, they will ask you to solve for the concentration of one of them. The beauty behind this is that at equilibrium, you have this right here. We can make an assumption that this is equal to that right there. What we can do is we can represent them by letters X because they are equal to each other. Because both values is the same, they can be represented by a single letter. X, Y, Z doesn't really matter. So what we can do is we can now have Kw equal to X squared, and we can solve for X squared easily by just taking the square root of that. So X equal to the square root of Kw, which in this case equal to H3O plus or equal to OH minus. And now we can find the pH or the pOH. And that's why when we look at the self-ionization of water, which we know at pH of 7, right? Which means we have the same values. So the next thing we are going to look at the dissociation of weak acid and weak base, and they have very similar formula. So what's the difference between acid and base? Well, Ka is for acid, Kb is for base, and we have the formula right there for you. And notice when we write the equilibrium constant, we ignore water, and here we have our acid. Again, it will break into hydronium ions and the conjugate base. So you can see that we can rewrite it right there. Same thing for the base. So be familiar with it. It doesn't matter what base or what acid, as long as a weak base and a weak acid, it will have the same formula. So keep that in mind. That's why we use the letter HA, and here we use the letter B. So once you write the equilibrium constant, the same thing with the at equilibrium constant, you have this right here. We had to make that assumption. That's the beauty behind that. We can use this to represent by X and X as well. And in most cases, it will be given to you in these values. The Ka and the concentration of the acid will be given to us because we can actually use it in our lab. We know what the concentration is going to be. We don't have to find it. It's given to us. The same thing for the base. This, at equilibrium, we can see that the same thing for the weak base. We can make an assumption, well, not really assumption, but the reality is this right here. At equilibrium, this is that equal to each other. So therefore, we can represent that by X. Well, we can rewrite that in terms of Ka equal to X times X divided by HA. Remember, this is values given to us, or equal to X squared. And we're going to solve problem based on this understanding. See how easy that is? So the same thing for Kb. Even though we change it, the concept is still the same. Kb equal to what? X times X divided by B, concentration, which is given to us. So we have X squared over B. That's the logistic of how to use this formula. Here's another thing that we have to realize is that once we find the concentration of OH for base or the concentration of H plus for acid, in this case, we can determine the pH right here. And down here, we can determine the pOH. So remember, base, you had to find the pOH. For acid, you had to find the pH. That's the only way you can do it. But once you find pH or pOH, you can solve for the other one because we know that pH plus pOH equal to 14. And here's another one. Because when we work with water, right, this is for water, we can actually find the Ka and Kb of either one. So Kw equal to Ka times Kb, or we can look at Kw, pKw equal to pKa plus pKb. And again, this is for water. That's one thing you have to remember, because a lot of time they ask you for a water problem. And we already learned that once we have the pH, we can determine the concentration by take 10 to the negative pH. The same thing with pKa. Remember, P functions the same. P means negative log. To get the concentration, or the Ka, or the Kb, whichever your choice, we take 10 to the negative power of that P, okay? So this is extremely important because sometimes they ask you for the concentration, but this little information will make the whole entire thing complicated. Now let's solve this problem together. We are going to tackle the hardest problem first. Let's look at one of the most challenging problems out there, and that is we have caffeine is a weak base with Kb of these values, okay? Without using a calculator, estimate the pH of a 0.1 molarity solution of caffeine. Why is this so tricky? Well, first of all, it gives us a weak base, but it's asking for pH. So you cannot do that directly. We have to use pH plus pOH equal to 14. So you have to find that first in order to solve for pH. So let's look at this. First of all, we don't really care what's the formula for caffeine. It could be any common K you want. It doesn't really matter. But I can tell you that it is a base, okay? And we know that, going back up here, a base has this generic formula. So BH plus OH minus, the same formula, okay? It doesn't matter what it is. It will always follow the same steps. And we know that KB is equal to, look at that. We just write this right here. BH plus equal to OH minus over B. There you go. Which we know is given to us. I promise you it's given to you, both the values right there, right? And we can make an assumption that, again, at equilibrium, both of these values is the same. So we know that BH plus equal to OH minus. So we can represent that by letter X, okay? So now we can put an X for those. So X is equal to those values because they are the same. We can use Y, Z, it doesn't really matter. Now we are going to plug everything in. So we have 9 times 10 to the negative 4 equal to, I'm not going to write this formula, I'm just going to write X times X equal to the values of my base right there, which is 0.1. There you go. And in this case, we're not going to use calculator, okay? We are going to do this without calculator. So what's this going to equal to? X squared over 0.1. Okay, so we can kind of ignore that part. So now we have 9 times 10 to the negative 4 times 0.1 equal to X squared. Well, look at this one. This is not very useful to us, so we have to rewrite this times 10 to the negative 1. Okay, because it's one decimal place over. So we multiply this and this together. Basically, you add them together. Now what do we have? We have 9 times 10 to the negative 5 equal to X squared. That right there, okay? So how do we turn X squared into X? Well, I'm going to change different color first. What we have here is we can take the square root of both sides. Okay, so we can ignore the 9. Okay, again, we are doing this estimation. So we can do this in terms of 10 negative 5 equal to X. Well, how does that really work? Well, the square root is equal to a number to the 1/2 right there. So in this case, we have 2 times 1/2, and then we can remove that, times 1/2. So what's that going to tell us? Well, this cancels out equal to 1, right? And 10 to the negative 5 times 1/2, that is 10 to the negative 2.5. There you go. This is your concentration for the OH minus, which is also equal to your BH plus. But we don't really care about BH plus. We care about this because we're looking for pH. So what we can do is we can look for pOH right here. pOH equal to what? Well, P negative log of 10 to the power of negative 2.5. Okay. Here we will learn that log with a base of 10 to the same base equal to the number is equal to the number. So in this case, pOH is equal to 2.5. There you go. See that? Because this negative and this negative kind of cancel each other out. So now we find our pOH. Guess what? We know that pH plus pOH equal to 14. Okay. So we have pH equal to 14 minus 2.5. What is that going to be? Well, that turned out to be 11.5. There you go. So if we are estimating this, this is somewhere between 10 to 12, okay? See that? It's our estimation. But as you can see, we had to do a lot of mathematical problem here because we had to know how to use log. We had to cancel out square root. That's what makes this problem so difficult on your AP Chem test, because they're not letting you use calculator and it's driving you crazy. But if you can use a calculator, life would be a lot easier. There you go. Now let's try another problem. In this case, we said estimated Ka of a 0.01 molecular solution of a weak monoproduct. That's just basically saying that has one hydrogen acid right there, has a base, has a pH of 4.0, and we only ask to enter the power only. So we know that, again, this is a weak base, and if you don't want to write this part out, you just want to go straight to this, which is given to you right there in your formula sheet. Okay, so we know that Ka, okay, Ka, well, in this case, weak acid, so we are looking at this one specifically right here. That one right there. The acid part right there. Okay? So let's go down straight and do it. So in this case, we just write down Ka equal to H3O plus equal to the conjugate of it divided by HA. There you go. And again, this is given to us, check, and we are looking for that. But in this case, we don't know anything about the concentration of this. And remember, they are the same values, okay? They are the same values. But what we know is pH. What does pH give you? Well, pH give you H3O plus concentration there. Remember pH, okay? If we have pH equal to 4.0, to get the concentration of H is really straightforward. It's just equal to 10 to the negative of pH right there, which in this case 10 to the negative 4.0. Remember that shortcut we've shown you right here? This part is where a lot of people got tricked on the AP test. If you don't memorize these basic facts, you are going to have a very difficult time, okay? So in this case, the concentration of H3O plus, which is the same thing, concentration of H plus, is equal to 10 to the negative 4. There you go. Now we can plug it in, right? Because what we know is this right here is the same, also equal to the concentration of conjugate base right there as well. So let's plug it in. So we have equal to 10 to the negative 4. And what makes this even more difficult is that we have to do this with our calculator. So we have 10 to the negative 4 times 10 to the negative 4 divided by this one right here. Okay, this is not going to be useful to us. We have to rewrite this in terms of that. Okay, so it's 1, 2. So basically 10 to the negative 2. There you go. 10 to the negative 2. Okay, and now all we have to do is simplify this. What we have here is equal 10 to the negative 8 divided by 10 to the negative 2. Well, that is equal to 10 to the negative 8. We bring this up, which means we take the reverse of the exponent, times 10 to the second. And when we multiply, we add them together. In this case, 10 to the negative 6. And there you go, 10 to the negative 6. So how else can I make this problem tricky? Well, of course, I can give you a weak base and then give you POH, and you do the same thing, okay? So as you can see, for this type of problem, they have so many different variations, and you really have to figure it out. Let's try the last one. What is the pH of 0.001 molarity of a weak acid given Ka equal to that? So the same thing, this is a weak acid. We already memorized it already. Ka equal to H3O plus times conjugate base. And again, this formula it will be given to you on your formula sheet if you don't remember. Just find Ka for weak acid dissociation. So in this case is HA. There you go. And what we are going to do is, again, we are going to find the pH, which right here we have to find the concentration of that one right there. So this is a lot easier than the first one we did. So what we can do is X times X. Remember, we know that these are equal to each other at equilibrium. So we have a Ka as well, which in this case 4 times 10 to the negative 10. See that? And we also know the values of the acids given to us. Well, this is not going to be important. We have to rewrite it. 1, 2, 3. Okay? So in this case, times 10 to the negative 3. So 10 to the negative 3. And there you go. We're going to bring this over here. So we have 4 times 10 to the negative 10 times 10 to the negative 3 equal to x squared. So we can simplify this. You can add it together, okay? So we have 4 times 10 to the negative 13 equal to x squared. There you go. See how that works? So what can we do? Well, to do this, we have to do the square root of both of them. Again, we can ignore the 4. So what we have here is 10 negative 13 times 1/2. The same thing over here, 2 times 1/2. Cancel out, right? So x, what's 13 divided by 2? So that's, look at 6.5. So in this case, we have 10 to the negative 6.5. There you go. And this is the concentration of H3O plus, or the concentration of the conjugate base. But all we care is about that one right there, because the negative log of this right here, which in this case 10 to the negative 6.5 equal to 6.5. There you go. So this is our estimation right here, okay? So it's at about 6.5. And that's pretty much how we combine everything together right here, okay? From this information to the equilibrium constant of a weak base or a weak acid and relate them together. So in this case, what we can do is, again, if I want to solve for POH, we just take 14 minus that gives us POH. And here's is what make it even more tricky, is sometimes they give you a pKa, and then you have to find your Ka from there, or sometimes they give you your pKb, then you have to find something from there. It depends on how tricky the problem is, but in most cases, hopefully it gives you this type of format, and then you can work from there. But don't get tricked, okay? Remember P, and how does that relate to Ka? It's just very basic information. If you are going to struggle, write this down. This is where a lot of people struggle the most. How do you get from pKa to Ka, or Ka to pKa? In most cases, pKa to Ka, okay? And as always, take the time to solve the problem one step at a time. And then if you have any question, take a picture of your work, put in the forum, and we will do our best to support you. And we see you next time on another exciting chemistry lesson.